Good. Okay, so welcome to this lecture. What we will see today is the notion of duality. And we will see duality first for nonlinear problems that are not necessarily convex. And we will see what happens for convex problem and why duality for convex problem actually gives you many more information. So if you want to study duality in general, then we can start with the very general problem. So I will write a minimum here. So to simplify the expose, I will not necessarily worry about whether the minimum are attained or not. So at the beginning of the lecture, I will kind of always assume that when I write minimum, minimum exists and is unique, just to simplify the discussion. But of course, there are a few cases to consider, but we will simplify. So we consider a problem like this. So we have a function f, which may be any nonlinear function, and here other scalar function fi, which may be any scalar nonlinear functions. And here the problem is you need to minimize this function under these constraints. And x is some vector of real numbers. Okay? And so the minimum of this function we will say that there exists a minimum and that it's unique, and we call it x star, just to simplify. Okay, so we'll first see what we like to call the Lagrangian function in optimization. So first notice that in a kind of artificial way, you can rewrite this problem using the indicator function. So you could say this is the same as minimizing this function without constraint, where you have the indicator function bigger? Yeah. Okay. So here the indicator function is defined like this. So the indicator function of a set S is defined as being equal to infinity if x is not in the set, and to 0 if x belongs to the set. Okay, so you could somehow rewrite it like that. This is not a fundamentally crazy idea, but you could do it. Now, what is less obvious is that you could rewrite it like this. Now we should be a bit careful. Y should not be completely free. I might say that yi, let's say, is positive. And if I say yi is positive, I should here put a plus, yes. So depending on whether you put negative or positive here, it should be minus or plus. So there are different conventions, and yeah. But can anyone see why you have this equality, that this is equal to this? So if you want to simplify, you can actually, you don't really need this minimum. You can also just say that you have this equality for all x.
Oh, because you can make yi arbitrarily large to make it so minimizing, or if we had a minimization on the other side, we'd still, if we have that huge max, it's kind of equivalent to having an infinity and multiplying it out.
Yeah. Mm-hmm. Yeah, I should put a 0 there for later. Exactly. So in fact, what you can see is that the indicator minus of a number, where x is some scalar number, is always equal to, and here I will write supremum because it can be infinite. Because suppose x is in R minus, if x is in R minus, so if x is negative, then here in the supremum I will want, because because y should be positive, the maximum of this expression is taking y equals 0, and so this will be 0. So it works. And if x is positive, then by taking y arbitrarily large and positive, I can get as close as I want to infinity. So you can see that this function is actually equal to this indicator. Okay? And so this way of rewriting the indicator function is really the canonical way to find the Lagrangian function, because I didn't tell you, but this is what we call the Lagrangian function that we like to write L, for instance. Okay, so whenever you have a problem with constraint, you're going to rewrite your constraint as indicator, and you will replace each indicator by some linear form like this, using this kind of tricks. And once you have an indicator function, you are going to look at your problem in a different way. So one useful way to think about this is as a two-player game. So I briefly review. So here we have the Lagrangian function, which is in this form. But for a moment, forget about the fact that it's in this form. Consider any function L. So if you have a function L that maps, so you have a set of x, a set of y, any set, any function L, to real numbers. Okay, and so given xy, L of xy is anything. And you can think of this as a game. So you have player 1, x. The set x is all the possible action of player y, and the set y of player 1, and the set y is all the possible action of player 2. Okay, and once the two players have played, the payoff is L. So there is only one payoff. So this is why we call it a zero-sum game. So the player 1 he wants to minimize L, and player 2 he wants to maximize L. Okay. And so this is called a zero-sum game, because when player 1 is happy, player 2 is not happy, and whenever player 2 is happy, player 1 is not. So they're really like completely conflicting interests. And so when you have a game like this, you can you can study the case where one of the two players plays first. And then the second player actually sees the action of the first player, and then he only plays after that. So suppose player 1 plays first, and he knows that when after he's going to play, the player 2 will see his action and then play. So in that case, the player 1 says, when I play X, what am I going to get? So when he plays X, it means that for player 2, it will maximize the payoff. So he knows X, and then he would take the Y that maximizes the L function, because player 2 wants to maximize. And so f of X will be what player 1 accepts to get when he's playing first and he's playing X. And similarly, we'll define G of Y, which is what the player 2 is expecting to get when he plays first. So when player 2 plays Y, then after that, player 1, he will do this. Okay? And you can, and to simplify, we will always assume that this maximizes attain as a, let's say, unique number. And so we will say that Y bar of X is the unique argmax of L xy. And we will write this. And this is just to simplify the notation. Of course, there could be several minimum and several maximum, but this is to simplify. And so then you can actually write this. It's a bit simpler. Okay? And so y bar is the optimal action of the player 2 after he sees that player 1 plays X, and X bar is the optimal action of player 1 after he sees that player 2 plays Y. Now the question is it better to play first or to play second? What do you think? Yes?
Second, because you have information about the previous link.
Exactly. So somehow it's kind of intuitive. It's always somehow better to play first, because when you play second, it's because when you play second, you have information, and you can adapt to the other player's move. So playing first is never good, and you can actually show it if you want. And it's good to have this geometrical view. So let's assume that X and Y are just scalars to make it easy to see in 2D. And so this will be the set of action X. This will be the set of actions Y. And for each X, there will be the optimal action of player 2. And so maybe this is something like this. And this is X, Y bar of X. So for each action of X, we have the corresponding optimal action for Y. Do I have color? No. And then you also have this function, which is okay. And so somehow for player X, if player X plays first, so f of X is actually, if you think about f of X, it's actually the value of L along this line. So if you want to find f of X, you look at the X you're at, and then you look at the corresponding point here, and you look at what the value of L is on that curve. Okay? So f of X is looking at the function L along that curve, and g of y is looking at the function L along that curve. And so when you solve this problem, if you want to go back at optimization, you're actually minimizing L, but only along that curve. So that curve is kind of the feasible primal dual set. And so in all generality, when you minimize f, you find some x star. So let's say x star is this point. And so it corresponds to, and this would be y bar of x star. And then if you minimize g, you will find some y star. Okay? And now what is interesting to look at is this point. What is this point? Here we kind of use the fact that our domain is just a Cartesian product. This is important. And because our domain is a Cartesian product, we can always, once we have these 2 points, we can always also look at this point. It's well defined for L. And what can you say about this point compared to this point, for which the value here is g of y star, and the value here is f of x star. What can you say about the value of L of x star y star compared to these two? Yeah. Here I didn't think about the fact that they cannot see both this one and this one at the same time.
Yeah. Use the slidey boards and then use the other 2 boards.
Yeah. So remember the definition of G and F. So maybe I write it again here. Remember that F is defined as the arg max So take some time to think about it, because that will help you play a bit with the definition and get some intuition on what's going on.
What was the high-level motivation of this? So are we trying to just, like when we convert it to Lagrangian, we would have unconstrained problems,
Yes?
right? Like, are you saying that this is what the solver does internally? So it's good to know how this works, or like what?
Yeah, so this kind of reasoning will actually give us anything like the KKT condition and so on. So yes.
The what condition?
The KKT condition.
Oh.
I mean, it will. This is the. This gives us weak duality, strong duality, and it actually helps you, yes, to. It's important to. What I like about this picture is that many times when you play with Lagrangian duality, you can get confused and do the incorrect things. So sometimes when you take derivative, sometimes you're taking derivative of f, so compared to this line, sometimes you take derivative of L. And so it's important to not get confused, to always have this picture in your head when you're playing with the Lagrangian function, because it's very easy to forget exactly what you're doing otherwise. But somehow here, we are not even in the context of optimization here. It's just any function L. So somehow, by definition here, y bar is the optimal move for the player 2 whenever you play x star. So it means that the move y star is not optimal, so it's worse, right? So because player 2 wants to maximize, and this is the payoff of the better move, what can you say between these two numbers? Which one is, yeah? Yeah, so L is smaller. And the same thing between these two. Which one is larger? Yes? G is larger. No, because player 1 wants to minimize. Okay, so player here x bar is the best move for player 1. And so it means this one is smaller. And so this is an important, something nice to see about weak duality is that so what is known as weak duality is this. You have that so when you solve the dual problem and you look at the optimal value, you will always get something smaller than the optimal value of the primal problem. And in fact, because this is the minimum of f of x, and this is the maximum of g of y. So if the maximum is a lower bound, it means, in fact, for any y, g of y is a lower bound. So for any feasible point y, g of y will be a lower bound. So in our context, we had this. And here, for any feasible point x, f of x is an upper bound. So this is weak duality. And what we see here is, in fact, you can say even more. You can also say that in between, you always have L of xy. So you have this guy in the middle that you can actually use. So here, this is a complete proof of the fact that you have this is called the min-max inequality. So in the context of any function L, this inequality is called the min-max inequality. In the context of optimization, we call it weak duality, but it's the same thing.
Are they supposed to be argmax and argmin, or are they max and min?
Yes. Okay, so in this context, so there is something very well known in game theory that was found by John Nash, is the concept of Nash equilibria. Somehow, normally in game theory, you don't have that one player is playing before the other one. They normally both play at the same time, and they don't know what the other one is playing. And in that context, it's quite hard to know what should you play, right? But then Nash defined point that are a bit particular, because it's points such that if you knew the other one would be playing that, it's a pair of strategy. Let's call them x tilde y tilde. Suppose you have a pair of strategy x tilde y tilde, so that if you know that the other one is playing, if you know player 1 is playing x tilde, then you are going to maximize this. So if you know the player is playing x tilde, then you want to play y tilde. And if you know that the second player is playing y tilde, then you want to play x tilde. No, this is xy. So if you have a game like that, and the two players are very intelligent, they will know that there is this situation. And so somehow, if you know that the other player plays y tilde, then you know that you should play x tilde. And if you know you play x tilde, then he knows he should play y tilde. And so somehow, if you think the other player is playing y tilde and you think you're playing x tilde, you will just both play x tilde, y tilde, you see? So this is why it's called an equilibrium, because if you're thinking he's going to play this, then I need to play this, then he's going to play this, then I'm going to play this. If you look at this dynamic of infinite thinking, then you actually converge to some equilibrium of thinking. This is why it's called an equilibrium. And so these Nash equilibrium are actually a pair of moves that good players should play somehow.
That's regardless of who starts first, doesn't matter?
Yes, it's when they play at the same time. And somehow, if one plays first and the other plays second, if you play x tilde, he's going to play y tilde, and if you play y tilde, then you're going to play x tilde. So when you have a Nash equilibrium, then playing first or second is not so important anymore.
But I don't understand what you mean by play by the same time, because you need to like fix one of the variables, right, to do the optimization. So isn't that alternating?
Yeah, when you write the optimization like that, yes. But suppose that you cannot really write it mathematically like that, because it's suppose you will try to pick some x, your opponent will pick some y, you don't know what he's going to pick. And then once you see what the two opponents played, you will look at what is L of xy, and this is what the payoff that you will get. So you cannot write it as an optimization problem for either player, because they don't have full information on what the other one is going to play. So it's like the first player is going, okay, I need to minimize over x L of x y, but here y is not defined in the expression. You don't know what's going to be y. So you cannot solve a problem. It's like you don't know what's going to be y.
So then why is this a good model for that situation? Because they can't do optimization on y, right?
Yeah, I mean, this is why game theory is a very complicated topic, because it's not an optimization problem. When you study game theory, you don't know what they're going to play. When you have a Nash equilibrium, you think, oh, they should play that, but otherwise, yeah. But somehow in the case when there exists a Nash equilibrium, and it's not always the case. For most function L, there is no Nash equilibrium, but when there exists one, then they can play this. And so when there is a Nash equilibrium, it's not better to play first or to play second. And so G was the payoff when player 2 plays first, and this was the payoff when player 1 plays first. And so when there is no advantage of playing first or playing second, this is when G of y is equal to f of x. So in that situation, playing first or second, doesn't matter. And when you have this, this is called strong duality. And in that case, you have equality here and here. And this is what's always a bit confusing with Lagrangian duality, is that when you look at strong duality, what the information when you have strong duality is that you have equality here and here. Is that when you have strong duality, then x star is the best move for y star, and y star is the best move for x star. Okay, so whenever you have strong duality, what you know is that x star is x bar of y star, and x bar okay, so you have that x star is the argmin of L of x y star, and y star is the argmax of L of x y star. And this is also why it's called a Nash equilibria, because if you start from any point, let's say some point x, and then you apply y bar, then x bar, then y bar, then x bar, and you continue like that indefinitely, you will converge to the Nash equilibrium. Or you will converge to the, so if you wanted, you could solve optimization problem like that. But, and then you will converge to x star, y star. And what's interesting here is that when you say that x star is the if x star is the argmin of L of xy, suppose L is differentiable, then what can you say? Yes?
X is a local minimum.
Ye-
Local minimum.
Yes? And so if you know L is differentiable, what can you say if it's a local minimum?
Zero. Zero.
Yes. And so you can say that the gradient of L you have that if you take the Lagrangian, you differentiate it only with respect to x, and then you evaluate at x star, y star, you know this is 0. Because of this fact. And from this fact, okay? And so these two identities, this is what gives you what we call the KKT conditions. So whenever you have a problem, an optimization problem like this, you write the Lagrangian, and then once you have the Lagrangian, you look at these gradients, and these give you the KKT condition, which are the condition in order to have strong duality to hold, and to have these points are as the optimizers. Yes.
I understand this notation because if you have x star and y star
Yes, exactly. So that's a very good question. So you should understand it like that. So you take the elk function, you differentiate only respect to x, and then you evaluate. You see, so if you want to write it differently in a more explicit way, and this is very important to do it. So you take the function that maps x to f L of x y star. You take this function. You take the gradient of this function. And then you evaluate x equals x star. This is a very good question because this is very important to do this right. Otherwise, you will not get good conditions.
That's what you mean by gradient subscript xl is what you have up there?
Yes.
You have y star.
So somehow here in this function, y is a constant. So when I say the gradient of this, there is only x as variable left. And so it's clear that you only differentiate with respect to x.
So it's like the partial derivative of L of x with respect to x.
Yeah. Mm-hmm. So you could say you take L of xy, you differentiate with respect to x, and then you evaluate at x and y. Okay?
So I think like the reasoning why this matters is because sometimes it's easier to solve like the dual problem than the primal problem, right? That's why we care about all this, right? Because we want to reformulate the problem as the dual and then solve it, and then we can use weak duality. But if we actually want equality, it's easier to prove the KKT conditions than to actually solve the primal problem? Is that what you're saying here? Or like what's the how is this used? What
Mm-hmm.
usefulness of
I think I will give an example just now. So it can be useful in many different contexts. But one way Lagrangian duality is used is just to actually find what is the dual. So there is one example which is very important, and for which it's not very easy to get the dual, and you actually need to do these kind of things. So I think I will go straight to that example. So suppose you have this problem. Suppose you have a problem like this. So this is a conic, you have conic constraints, and then you have a quadratic objective, okay? And you want to get the dual of this. So it's not, usually when people take duals, they know by heart like dual of LP, dual of conic, but dual of quadratics, usually you don't remember what this is. So first step was the Lagrangian. So you take what will be here? Yes?
The sum of yi times, I guess, xi, or f of x, fi of x.
Mm-hmm. So in this case, it's aix. So you want to rewrite, so it's easier to do in several steps. You have the indicator function. So how can you rewrite this indicator function as a supremum of y of, what should be y? It should be the domain here. So you have Ki is a convex cone. Whenever z is in Ki, this supremum should be 0, and whenever z is here, the supremum should be infinite. Yes?
Y is an element of the code. It's an element of K.
Y is what?
An element of K.
Do you know what is the dual of a convex cone? Oh, okay. Very good. So in fact, here we actually need some set here. We actually need a set such that whenever z is in the cone and y is in that set, then, so here I will write a minus, then this should be positive. So if whenever z is in that cone and y is in that set, this is positive. Then, because you want the supremum of this, you will just choose y equals 0, and so this will be 0, and so it's like the indicator. And then whenever z is not in that cone, like here, there should exist some y such that this is not positive. And so you can have here plus infinity. Okay, so suppose this z is not in that cone, then there exists some y in that set that we are looking for. So we will call it the dual that we write k star. Whenever z is not in that cone, there exists some y, which you can see as an hyperplane. Okay, because y transpose x defines an hyperplane in the space of y vectors. An hyperplane that shows z, that separates z from this cone. So somehow you will define the dual of k as the set of y such that y transpose z So by that definition, with this definition, you see that, so in the dual, you will have all the vectors that are always, for which the scalar product with any vector of the cone is always positive. So with this definition, you are sure that whenever z is in the cone, this supremum is 0. And the fact that whenever z is not in the cone, this supremum is infinite is the fact that k is convex. So because k is convex, this implies that for all z that are not in the cone, then there exists y such that y transpose z is negative. And this is because k is convex and closed. All right? So this notion of dual of cones, you can see it exactly what we need to generalize what we had. So we want to generalize this. And to generalize this for any conic constraint, exactly what we need is this definition. And so in fact, this definition was defined by the mathematician before we actually needed to solve conic program. But if it wasn't defined yet, we would have defined it just now. OK, so here what we have is this. And in the domain, x is free, and yi should belong to the dual cone. All right, so now we have the primal program. This is the primal program. So this minimum is what we call f of x. What we want is what is the dual. So there is this dual, so some function that only depends on y. And that will give us always lower bound to our primal program, right? So for any feasible y and feasible x, you always have this inequality. And you want to find this dual program. And you know this dual program is defined as dual program is defined as whenever I pick some y, I look at what's the best response for the first player. And so it means that so we define it, remember, like this. And so to find what is x bar, we will use this identity. So you compute the gradient of the Lagrangian with respect to x. And if you do that, what you get is, so the gradient of this is qx. And so I know that this is 0. So I have this identity. And so this identity gives me a way to find x bar of y if Q is a positive definite matrix, I can so if in your QP Q was invertible, so usually we're interested by convex QP because these are convex programs. In that case, usually Q is has all its eigenvalues that are strictly positive, and so you can actually take the inverse of Q. And so you can actually find explicitly this x bar of y. And so you actually have this trajectory exactly. And so to find G, you just need to look at what's the value of L along this trajectory. So let's write it here. So this is the value of L. And now I can just replace x by this. So what do I get? I get so let's maybe call this z. Let's say z equals sum of the ai yi minus a0, just to simplify the notation. So this would be z transpose so here I have replaced it here. Then notice that here you have minus x transpose z. So this is so there you have minus so this is L of x bar y, and so this is in fact g of y. And you need that yi belongs to the cone ki. Okay, so if you solve, so notice that here there is no x anymore, only y. So if you solve this for y, this is also a QP. You have a quadratic objective and you just have conic constraints. And if you solve this for y, you will get so for any y you get a lower bound, and if you solve this to get the maximum value of g, you will get the best lower bound. And if strong duality holds, this will be actually equal to what you would have obtained if you were solving this problem for x. And if you take the optimal value for y and x, and you combine them, and you look at L of x star, y star, you should get something that is between g and f, and if strong duality holds, it will actually be equal to the two of them.
So is this case where it's easier to solve the dual and then show the KKT conditions than directly solve the primal?
what you can do, what most solvers do, is that they solve the dual and the primal at the same time. Why? Because if you solve the primal and the dual at the same time, you have both of these equalities. And sometimes it's easier to do it like this because you can use the information for both primal and dual. So I'll give you a very explicit example which has a bit of history. So who knows what semi-definite programs are? Not yet. So let's introduce semi-definite programs.
Use the other boards, because otherwise you're going to end up covering yourself again.
Yeah, but I don't need these. Maybe I can start with this one. I think I'm done with this one. Okay, so semi-definite programs. They're defined like this. Okay, so here, C and the matrices AI, these are symmetric matrices. Okay, so they belong to n by n matrices, and they are symmetric. So the elements of both sides of the diagonal are equal. And X, it's also symmetric, and it's so positive semi-definite. So X is what you're looking for. So you want to find a symmetric matrix that is positive semi-definite, and that satisfies these linear constraints, and that minimizes this objective. And so if you want to get the dual of this program, you can do similarly to what we did here. So you will want to do you want to write the Lagrangians. So here so you want to solve trace of Cx plus the sum of the indicator of 0 of trace of AIX minus BI. In this case, what can I replace the indicator with? Because here they should be 0. In fact, I can replace it by the supremum for yi, which is 3. So if this is 0, this supremum is 0. If this is non-zero, this is positive infinity. So in this case of equality, and in fact, the domain of y should always be the dual of the cone that you have. So Remember at the beginning here, in fact, this cone was R minus, and the dual of this cone, this is a one-dimensional cone. The dual of this cone is itself. So if you take R minus, you take the dual. This is the dual of the negative numbers is the negative numbers. And if you take the dual of the set with only 0, you know what this is? No. So it should be the domain that we choose here. What is the domain here? Any real number. So the dual of the set with 0 is just any real number. And you have this, and you also have that the dual of the set of real number is the set with 0.
Sorry, could you explain what the dual of a set is and how that's?
Yes. So we can go back to the definition, which I erased. So whenever you have a set, that should be a cone, otherwise there is a bit weirdly defined. It's a set of y such that yx is positive for all x in the cone. So if you take x, if you say k, which is the set 0, what is the set of y such that y is times all the numbers that are 0, so 0? What is the set of y such that 0 is greater than 0, basically? Yes, everyone. So this set, if k is 0, this set is all the real numbers.
Yeah, is that a norm?
Hmm?
Is this a norm?
Sorry. Scalar product, yes. So if this is a set with only 0, this is basically only need to hold for 0. So, and if this is the set of negative numbers, let's say, then what is the, so here it's scalar, so I don't really need the transpose. The set of y, such that the product of y should be positive for every negative numbers. So that's all the negative numbers. And here, if this is positive numbers, it's positive numbers, and so on.
So if x is, or if k is the set with 0, the set of y can produce positive dot product
With 0.
with 0. Okay.
What are numbers when multiplied with 0? They are non-negative, all numbers. Okay, so this is the Lagrangian. And so now we want to find what the dual is. And so what we do is that we will want to eliminate x from this expression. And so usually what you do is that you rearrange to put all the x at the same place. And so this, in the Lagrangian, this is equal to trace of C here I could put plus or minus. It doesn't. No, it does matter. I should put minus. Because the supremum is inside, right? So I will just write this.
Sorry, so the supremum is an inner maximization here? Is that what it's
Yes, but you can move it out. So now you can do this.
Yeah, so if the trace term, if the trace plus bi is negative, then the supremum, like the best y value would be 0, right? But that's not allowed. We need equality. Am I misunderstanding how the supremum works?
So here, if you are the first player and you choose an x such that this is non-zero, see this is non-zero, then what the second player do is that if this is, let's say, if this is positive, then he will take yi, which is plus infinity. And so this expression will be plus infinity. And because you want to minimize, you won't like that. So basically so you don't want to allow the second player to put this term to infinity. And because the second player can choose any y, the only way to prevent him to put this term to infinity is to put this term to 0, right? And you can rewrite it like this. I misused the board again. I thought let's not do the same mistake again. Let's start with the middle board, but it was the same mistake again. Okay, let's assume we know that. So now if you want the dual, you should reverse the min and sup, because the dual is when the second player plays first. And so you have the supremum of y, the minimum, PSD, of trace Okay. So suppose you are the second player. So if it happens that this is, suppose that C minus belongs to the should have a minus that got lost. I think my y is if this is in the dual of the PSD cone, then what will be the choice for x? Yes, if suppose this is not in the dual of the PSD cone, then we saw on the part that I erased is that for a convex cone, whenever you are not in the cone, there is an element in the dual that will separate you for the cone. So basically for all the elements in the cone, then whenever you take a scalar product of the dual with that element, it will be positive. But if you're not in the cone, there is an element such that the scalar product is negative. And so if you are in the set, in some set that we don't know what it is yet, such that the dual of the set is the PSD cone, then if you are not in this set, then there will be x such that this is negative, and then because this is a cone, you will find a way to make this as small as you want, and so this will be minus infinity, and so the second player is not happy. So the second player, if he doesn't want to allow the first player to do that, he will always need this to belong to this set. And in fact, the PSD cone is quite special because its dual is itself. So this set is simply the PSD cone. Long story short, the dual is so this is the dual program, G of y. Okay. So now we will see why it's helpful to solve the dual and primal at the same time. What do we want?
The positive semi-definite, like that's a constraint on x, right? Enforcing that it's positive semi-definite.
Yes. So here, because it's a constraint directly on the variable, we just put it in the domain. You could see, you could put it here instead, and this would just be equivalent. The math would be different, but at the end you get the same result. So maybe you get more variable in the dual, but then you can simplify them because it's trivial.
Can you repeat the question?
So why do the constraint on x, what do we put it here? And why don't we, in the Lagrangian, add plus indicator PSD of x and try to do something? If we had done that, what would have happened is that here you would have had plus the trace plus the supremum, or minus the supremum of trace of zx where z is PSD. And in fact, what you would have also found and so the dual would have been this is equal to z, and z is PSD, which is equivalent. It's just you introduce a new variable z. But this is a good transition because I was going to introduce z. So whenever you take the primal and dual and you do the KKT condition, you find this equation. I won't go into the detail because we don't have time. So if you want to solve an SDP program, so you want to find a y such that this holds. You want to find an x such that this equation with a and b holds. And if the constraint that x is PSD, this equality holds, and this holds for y, and this also holds, then you know that x and y are actually the optimal value. So it just, if you take the KKT condition for the SDP, it's the feasibility of x and y plus this. And the problem with this is that it's nonlinear. And so for SDP solver, basically, the reason we have so many different solvers for this kind of problem is that there is many different ways to handle this constraint. So the different ways are basically how you linearize them. And so now I'll give the code for the attendance, which is why Nesterov? Because Nesterov showed around 30 years ago, he found a way to solve SDP programs. And what he did basically is that he said, look at the set, the feasible set of X. So we've got AI, the sets of X such that this is BI and X is PSD. And then if you look at the X that minimize transpose CX, you would find, let's say, this point. And what he says is that basically, suppose that instead of minimizing this trace with this constraint, you add in the objective, you add plus mu with a positive mu. So if you put this, then whenever x, and then you can forget about these constraints. Whenever x is not PSD, this would be minus infinity, so this would be plus infinity, because you minimize, you won't like that. So whenever x is PSD, then this would be some finite numbers. And whenever you will go close to the boundary of the PSD cone, this will go to infinity. And so when you solve this problem, you will find some solution. And the solution would depend on mu. If you put mu equals to 0, but still positive, whenever mu is positive, you cannot leave the PSD cone because this goes to infinity. But when mu is very large, somehow you don't really find the optimal solution because of this, which is affecting your decision. And so you look at what's the optimal solution for different mu's, and this is called the central path. This is the optimal solution for mu equals infinity. We call it the central path. Central, because it's central path. And this is the analytic center for mu equals infinity. And this is the optimal solution for mu equals 0. And so what Nesterov says is that start at the analytic center or somewhere close to it, and then move along the path like this. And when he moved, he was basically updating mu every time. And so he was saying uk plus 1 equals uk, and then he had some update. And he proved that basically at every time he would step up, he would do one step, you could decrease mu a little bit. And he has a way to decrease mu, so you were multiplying by some factor. But the problem with his method is that when you implement it in practice, so he proved that for all SDP problem, he could solve it in polynomial time. But then in practice, when he used it, the problem is that what happened for most instances is that, in fact, it was, so when you prove that it's solved in polynomial time, it's actually true. So the number of iterations he proved is actually true. You don't take more iteration, but you could take much less. Because when you could do complexity analysis, you already consider the worst case, and you try to find something that works even in the worst case. But you don't never have the worst case. Usually you have a very easy instance. And then he's very pessimistic. So he's in this very easy instance. He says, OK, mu is something here. I'll do one step. And then in my proof, I have proved that at least I can take this mu. And then the next mu I'm targeting is here. But because he's targeting mu here, he will step backward. And then he's targeting this mu. Then he will be here. And then he's targeting this mu. And then he will go backward. And so this was very slow. And then what people thought is, if you look at the KKT condition of this modified problem with the mu, it becomes like this. And so it means that if you solve the dual and primal at the same time for this modified problem, there is a way to do better than this. Can you guess what this is? So suppose you have some value of mu. Okay, you have some mu. You target the next mu, which is here. And you do a step towards it. But then you do a very good step. And this is the new x, the new z, the new y, and the new z that you can easily get for y. And then if you're very pessimistic, you know you have at least this mu, but you are way further. So it would be good to know where you are, kind of in the central path. How could you know? And basically, this equation is satisfied on the central path. So whenever you are on the path, if I take this point on the path for a certain mu, let's say I have some mu tilde here. For this point on the path, you have that this equation, you have that the trace of x tilde, z tilde is mu tilde I. So what they thought is that if you are here and you're not too far from this path, this equation does not really hold, but it's close. And so if you take the trace on both sides, the trace of the identity is n. And so you can divide by n, and then you get an estimate of mu. If you have x and z, you take trace of xz divided by n, and you get an estimate of mu. And so by doing this, they can estimate where they are. And that is very good because then they actually use the dual to solve easy instance much faster. So when they looked at the complexity, like how many iterations do they need, they actually, in the worst case, they need the same number of iterations as Nesterov, but in practice, it's way faster. Like no solver use Nesterov method. All solver, SDP solver are primal dual, and they try to find primal and dual at the same time because it gives you information about where you are. So this is to kind of give you the intuition of why it's useful to have both the primal and the dual in optimization. It gives you I'm already 5 minutes over, so that's it.